what we've avoided talking about to this point in the addition reactions is what happens if the reagent and the double bond are unsymmetric. Reagents can be symmetric or unsymmetric in terms of these addition reactions. Here we have an unsymmetric alkene. This carbon has an alkyl group here, and this carbon has a hydrogen group there. So these carbons are not exactly the same. And here we have an unsymmetric reagent. This could be HCl, it could be water, H and OH. A halogen is not going to be an unsymmetric reagent. If only one of these is unsymmetric and the other is symmetric, you only have one product possible. But when they're both unsymmetric, you can have two different products. We can have the X add to the group with the R on it, or we can have the X add to the group without the R. There's two possibilities. And so then we have to look at which one is more likely. Here's a table showing you these different reagents and alkenes. And when we say something is symmetric, we mean there's a plane of symmetry. So if we go between the bromine and the bromine, we see they're on the same on both sides. This double bond here is symmetric. The carbons have the same things attached to them on both sides. Over here we have examples of unsymmetric things. Through the double bond is what we're interested in for the alkene. And the hydrogen and whatever's on the other side is what we're looking at for the reagents there. You don't get both products. Regiospecific means that you only get one product forming. Regioselective means that one is favored over the other, but you will get some of each. It's really unusual to get equal amounts of both products, because when we look at the mechanism and how it adds, we see that the things that are happening are not the same. So if we're taking an alkene like 1-propene, this carbon has 2 hydrogens on it. This carbon and the other carbon in the double bond has 1 hydrogen and a methyl group. So this is unsymmetric. And if we're doing a hydration reaction where we're adding water, here we have the hydrogen adding to carbon number 1 and the OH adding to carbon number 2. And we get this product, which is 2-propanol. If we add the water in the other way and add the hydrogen to carbon 2 and the OH to carbon 1, we would end up with an alcohol still, but the alcohol group now is on carbon 1, and so this would be called 1-propanol. Don't be concerned right now with how that's named, but just recognize that these two compounds are different. They're not the same. And what we observe is that 2-propanol forms and 1-propanol is not formed. So this is a regiospecific reaction. We only get one of the two possible products. Markovnikov observed a pattern in how these unsymmetric reagents add to unsymmetric alkenes. And one way to state it is that the electropositive part, which is often the hydrogen of the reagent, bonds to the carbon of the double bond that has more hydrogen attached to it. So that's kind of hard to remember. So maybe a more colloquial way of saying it is, them that has gets. When we're adding this, the hydrogen is going to go to the carbon that has more hydrogen atoms already bound to it. So the carbon that already has hydrogen gets another hydrogen. Another way to think of it is, hydrogen is coming in here and it needs to choose between this one and this one. And so he's going to be more comfortable here because there's already hydrogens there. So he's like, I'm going to go here because my friends are already there. It's like when the Swedes immigrated to America. A bunch of them ended up in Minnesota, and a bunch of them ended up in Denver. There were probably other places that I'm not aware of. But, you know, you think of a Swede coming over, and they don't know anybody in America. Well, how are they going to decide where to go? Oh, well, I heard there's a whole bunch of Swedish people in Minnesota. I'll go there because I'm going to be more comfortable instead of going somewhere where there's not going to be anybody who speaks your language. So that's how I remember Markovnikovs rule, is that the hydrogen will add to the carbon that has more hydrogen. Now, that's not really a very scientific explanation, but it works. This is the scientific explanation up here. So what we see here, we've got, what would this be? 2-methyl, mom eats pickle, 2-methylpentene. If we hydrate that, the hydrogen is going to add to the number 1 carbon, and the hydroxy group will add to the number 2 carbon. And we'll get this guy with the OH on the 2nd carbon. We will not see this alcohol where the OH adds to the 1st carbon. So we'll talk about additions that follow Markovnikovs rule, and then there are also some that do not. And so we just have to remember, does it follow Markovnikovs rule or not? So let's do a couple of examples. Use Markovnikovs rule to predict which regioisomer predominates in each of the following reactions. So we need a formula, a structural formula, 1-pentene. Let's do this one as a condensed structural formula. So we've got 5 carbons, and the double bond is going to be between the 1st carbon and the 2nd carbon. So that 1st carbon is going to have 2 hydrogens on it. 1, 2, 3, 4, 5. This carbon is going to have 1 hydrogen. This is going to have 2, and then 2, and 3. This carbon has 2 hydrogens. This carbon has 1. We're adding hydrogen bromide. And so the hydrogen of hydrogen bromide is going to add to this carbon and not to the other carbon because of what Markovnikovs rule says. The bromine will add to the other carbon, and the product we'll end up with is CH3, and then this is CH with a BR on it. Does that make sense? Addition reactions to alkenes, I think of it as adding across the double bond. There's 2 carbons in the double bond, and each carbon is going to have an atom added to it. And Markovnikov says if there's hydrogens, more hydrogens on one, that's where the hydrogen side will go. So 2-methyl, 2-hexene. Well, let's try this one with a line structure. Hexene has 6 carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 carbons. 2-hexene says there's a double bond starting at the 2nd carbon going to the 3rd carbon. So that would be right here. And 2-methyl tells us there's a methyl group on the 2nd carbon. So I'm going to draw a line down here. So remember, this means there's a CH3 group down here. There's a CH3 group over here. This guy's going to have 1 hydrogen. This is going to have 2 hydrogens. These are not normally shown on the line structure, but I'm kind of shadowing them in there. These are the things that we need to see in our mind when we look at this structure. So then if we're adding H2O with an acid catalyst, we're adding, let's do a different color here, maybe that's helpful. We're adding HOH. And as this water molecule approaches this double bond to add to it, the hydrogen is looking for its friends. This carbon has a hydrogen bonded to it. This carbon has no hydrogens. So this guy is wanting to bond to that hydrogen. I'm sorry, that carbon. Which leaves the OH to go to the other one. Oops, I started the wrong way. So there's our 6 carbons. And we had a methyl group down here. The hydroxy group is going to carbon number 2. And we're not really going to, we wouldn't normally write it here, but that's where the hydrogen went. Any questions?
Doing this would get rid of the double bond in the beginning?
The double bond goes away.
Okay.
Yeah. Because what happens is these electrons move around, and this electron comes in and forms a bond with the OH, and one of these electrons joins in there, and then this guy joins with the electron from here. And so this double bond is broken, the second of the pi bond of that double bond, and this sigma bond is broken, and then we have 1, 2 new sigma bonds that are formed.